Welcome to the Graph Show. I have with me today Leo Meyerovich, founder of Graphistry, which is broadly speaking concerned with graph visual analytics, right? We'll be kind of talking about the intersection of graph AI and graph visualization today. Maybe Leo, you could just start by telling us a little bit about what you do at Graphistry.
Yeah, good to be here, Joshua. Thanks for inviting us. Graphistry has been fun. We're probably best known for our use of GPUs for accelerating the visual side of graph intelligence. And so people might have heard of Apache Arrow or NVIDIA Rapids. So we're kind of there on day -1 of a lot of that stuff. And so that lets us do visually explorations that a lot of folks can't. And then over the last couple of years ago, we realized that needed to actually go to get more operational, to start adding in workflow automation. So imagine for investigations, whether your customers, your accounts, or your security. And then over the last year, what's been really wild is actually the AI side of graph intelligence. So graph neural networks and universal manifolds, things like that. I'm sure we'll be talking about all of those things.
Yeah, sounds good. I want to get into graph AI a little bit. Sort of sub-symbolic approaches to graphs are definitely not my area of expertise, but it's definitely an important area these days. Maybe we could start there. Tell us a little bit about graph AI in Graphistry.
Yeah, so what we found is people start using Graphistry they might sense like, hey, I might have some graph insights in what I'm doing. And so, maybe they have like a Splunk query or a SQL query, and they kind of want to, I think there's like some graph insights I could get here. Like maybe there's some account activity I want to look at. And then very quickly, like if they knew a bit about graph, they might think, hey, maybe there's some like out of the box graph algorithm, like maybe a page rank or centrality that will tell them what's sort of important. Like maybe community detection, something like that. But as soon as they, once you kind of get into more specific domains, so let's say we talked about fraud before. So let's say we're talking about fraud scoring. They start saying, hey, well, I have some domain insight that, if someone's just trying to hold a bunch of credit card numbers, or I have like a flag list of accounts, that it's no longer about one of those classic graph algorithms, but it's like now I want to actually flow in attribute data to be as part of that decision, and I actually want to combine a bunch of those things. And so at that point, it's less about the classical graph algorithm, and it's more about starting to combining the graph shape, as in classical graph algorithms, but also the graph attributes. And that's what's kind of the exciting thing. I think we'll talk more about it, but the graph neural networks just finally started to become practical for a lot of these applications, and say about a year ago in reality. So it's been very busy there, I'll say.
Yeah, maybe we could try to pick a running example. If you want to start with fraud, let's start with a fraud use case.
And so let's talk about fraud, and then let me generalize why fraud is a good representation of other things, and then let's run with fraud. So fraud is a fun one because we have account behavior, and so that's people data. Often that people data is driven by machine interactions. So maybe you're on a browser or a web app and we have logs driving it. The account, like in fraud, we'll often look at things like maybe the account sign up, or maybe an account change setting, or a transaction. And so you can imagine all the log activities during those things. On the fraud side, we want to prevent bad behavior. We want to do like, is this a bad account or a bad transaction? If it was something like maybe a revenue opportunity, that might be like, hey, is there a lending score so that we might give this person more money? If this was something like a hospital scenario, we want to do a patient journey where we're trying to predict, not that you're changing an account setting because it's a bad thing, but you're going through a triage process, and then we're trying to predict the waiting time. So I actually like fraud because it's so representative of a lot of like that people data, digital data, behavior data, things like that.
Fraud is a good one because fraud use cases really require a human in the loop. At some point in my past work at Uber, there was always a human who had to review any potential instances of fraud and actually decide whether they're fraud and take action on them.
It's like a full team thing, right? Like it's not one, like a lot of times for graph, like they start siloed. So maybe there's an AI team who wants to do just an algorithm, or there's an investigation team who wants to do human investigation. And then fraud is just so far reaching that even if you start on one of those things, being able to do graph for the end to end and bring it into the full team, the full organization, like it is one of those cross-cutting things.
Sure, but I understand you don't emphasize graph databases for this analytics. You know, you say you can do the analytics without a graph DB. Graph DB might be nice to have, but it's not need to have. Can you go?
Yeah, so that's been a bit of a surprise. So and for folks, I guess following along, we put out this fun article at the beginning of the year. What is graph intelligence? And I think what or how the top companies are using it. And and it's a survey a bit about from how the academics were going, but also really looking into how it's been starting to get picked up in industry by, right now it's mostly top companies who have AI teams. And, you know, as Graphistry, we're trying to democratize it, but that's just like the current state. And so we're trying to kind of, you know, look ahead based on what those folks are doing. And one of my favorite examples there was this Chinese company, Meituan, probably mispronouncing it, so apologies. Think of them as sort of like a kind of like an Amazon or Google, where they do a lot of different things, a lot of like consumer stuff. And they have about 30 GNN graph neural network deployments, and they do have one graph database somewhere for some of their use case, but maybe one of the graph neural networks uses it, maybe none. And out of those 30, instead it's more of that classical modern AI pattern where it's more about the modern data stack, where you just get the data extract, and that could be a Parquet, it could be SQL, it could be whatever. And because you're running on GPUs and things like that, the graph database could be useful for like that one team doing whatever that knowledge graph stuff is, like I think is their use case, but it's not really relevant to, you know, having a, you know, graph databases are great. Like maybe you want to do like get a real-time 360, or you want to do some write heavy workload. But when we're doing a lot of the intelligence work, it's often or at least at the AI level, it's actually more of a slowdown for what you're doing. And from a data engineering team, if you have to have two databases now you have two systems of records, and it's like a lot of complexity. So most of the AI teams we see actually rather not work from a graph database if they can avoid it. But sometimes it's useful. So I'm not like an anti-graph database person.
Yeah, definitely. Sometimes it's useful. How would you contrast that approach with solutions like, you know, say Tiger Graph is really big lately on, you know, analytics where you do have a graph database in the middle?
Yeah, generally it's a slowdown. Like, I mean, they're never going to advertise it that way. But if you have to have like graph neural networks are running on these like big GPU boxes, and we're trying to do these really fast iterations. And so if you have to do a call out to a graph database, that doesn't really make any sense. Like you're just like, I don't know, you've gone from like nanosecond level to, you know, like your magnitudes beyond your performance requirements. What we normally see is the big, I mentioned Apache Arrow at the beginning. That wasn't an accident. Even before we're doing AI stuff, we wanted to get really nice throughput on this stuff. And so Apache Arrow lets us do these kind of like bulk export, bulk import, like zero copy, all that kind of stuff. That's kind of why we actually help create and implement a lot of the like initial stuff. And for the graph databases, I think the interesting thing there, not trying to get into the loop of an AI process. That's just going to break things and slow stuff down. The exciting thing for a graph database would be something like, could we do a bulk export, kind of like how from Spark and everything else, you can have this like really easy handoff through, actually like Arrow is native to Spark nowadays, like for a long time now. You know, catch up to that stuff, do bulk exports. Now, if you want to do your batch AI, or like real-time AI, you can get that really fast, even if it's like gigabytes or terabytes. Could we get that in seconds? Do our AI stuff, and then the other part is actually, could we do Arrow ingest? And so let's say we have a bunch of like feature vectors or scores that we want to update the graph database. Could we get that data back? So I know Neo4j and APOC, for example, they I think it's an APOC. They have a little extension for doing Arrow. I've talked with some of the folks in the TinkerPop community. I'm not sure where Tiger Graph is on being able to support graph AI in terms of like actual, you know, bulk import export, but you know.
Sure. Common to both worlds is a graph data model, I assume. Is there any common graph data model that you use across all these use cases? with?
Yeah. So it's useful. There's kind of yeah. Okay. So there's a few ways to think about it. Like what we find is actually it goes through a bit of a pipeline in practice. So let's work back from the algorithms, and we should talk about it maybe a bit more. But in particularly in real world business stuff where we have a lot of heterogeneous data, like we have like accounts and wallets and like all sorts of types of nodes. And then we have all sorts of types of data on it, like timestamps, values, maybe past scores, things like that. That it's very heterogeneous, and so for the algorithms side, a really great model. For example, I was just seeing for like fraud on the blockchain for Ethereum, RGCNs. Again, in the last year or two, they've become hardware accelerated, so they support the heterogeneity we want. If we think about it from a graph model side, that looks like a property graph. It'll be wide, maybe not super wide, but it'll be wide. So ultimately, so as input and also overall data model, a typed property graph is what we'd be looking for. The Apache Arrow, you might be familiar with like Parquet or something like that. That's the corresponding data format that would be efficient with it, and that a lot of the systems are optimized for. Now, internally, when we're doing the algorithms, one of the nice, like part of why graph neural networks are now practical is that one is, yes, we'll internally, for different indexed operations, they'll do the conversions to things like linear algebra. So RGCNs are about like actually having lots of little, like automatically, just to be clear, lots of little matrices for different types of data. And that'll use GPU accelerated stuff. But at the same time, for the Graphistry's work, we align with NVIDIA's cuGraph and Rapids ecosystem that we helped start. And then more recently, Amazon's DGL, Graph Neural Network library. And the reason I bring that up is part of what's happened is beyond just the traditional linear algebra style neural network stuff, at the same time, with NVIDIA's assistance, things like cuGraph and other more, like imagine like CSR format, those kinds of optimizations are in data representation tricks, more geared towards graph are getting put in. But importantly, that's sort of below, like you provide the property graph as just arrow tables or Parquet tables, but then the framework will help you with the multi-GPU or add a bigger than memory type of.
The term again, cuGraph, is that a K or a C?
Oh yeah, NVIDIA, everything is CUDA, so it's like CU and then whatever you want. Okay. And for folks not familiar with Rapids, you might be familiar with PyData, like NumPy, Pandas, Scikit. Mm-hmm. And what the Rapids stuff is about is it's a few cool tricks here, but conceptually, take your favorite low code Python data, like data wrangling, data science package. Same API, your Pandas data frame, but underneath have it actually run on one or more GPUs, one node, multi-node, same API, but it happens to run on those. And then because it's actually underneath CUDA shared libraries, their new language targets are showing up like JavaScript. And then because I was mentioning Apache Arrow, which is sort of this like interop format, you can actually, unlike distributed CPU systems, we're just moving data around, it's actually pointer passing. And so it's very like, we can compose across like, from data wrangling to data science to data visualization to AI, like without having to do as much data copying and data shuffling.
Okay, cool. Maybe just a slight tangent off on the GPU computing side. How do GPUs help with graphs?
Yeah, that's very non-obvious. So historically, they were horrible and data parallel computing was like graph is another name for graph is irregular computation, and that was one of the worst things for parallel computing. And starting around the 80s, people might remember Cray or the connection machine. The really cool thing that I think for graph that started was something called the segmented scan, which is the ability to take a tree and turn it into an array. And even if it's super nodes and things like that, you can actually have it, you regularize it. And so
like an adjacency matrix, or how do you turn it into an array?
More like a breadth first. So it's just like imagine the breadth first levels, and then and then a bit of an indexing scheme on that. But once you have that flattening, and then maybe if you have multiple attributes, those would actually be multiple distinct copies. Like if maybe we have like a timestamps and dollars, that would actually be two big arrays, but they'd be sort of paralleling each other. And so that was like in the 80s. And then in the kind of 90s and 2000s, the GPU stuff started happening, but that was really just reusing a lot of it. I'm grossly simplifying, but that was the conceptual thing. And then nowadays, as long as you think in that kind of bulk way, this is where things like pandas data frames are great. They get you thinking these kind of bulk operations. These ecosystems are working on top of it. In the AI world, there's also a bit of like matrix stuff going on, but at least from a user side, I actually found it's useful just to think of it as the bulk operation. I forgot your question there, but hopefully, I guess you're asking like, how does the
how do GPUs help? I don't quite get the segmented scan thing. I'm gonna have to look it up, but
yeah, like imagine before let's say we're trying to add some numbers, like it's intuitive on a GPU where if you have two big arrays and you want to do an addition, you could just have like this parallel, like pairwise addition. Once we turn trees into these big arrays, then we can start doing things like, for example, if I want to get the sum not over two lists of numbers, but the sum over a tree, I can now that I have this nice array and I know kind of have this nice level order, I can kind of do top-down traversal, bottom-up traversal. So
okay,
it's very regularized.
I see. Okay, cool. You mentioned property graphs in there. Property graphs versus RDF is kind of a theme on this show. So yeah. Why is the data model more like typed property graphs as opposed to RDF?
Yeah, I think it's because AI, as smart as it sounds, is pretty dumb. So even though it's very effective, it needs a lot of handholding. And so when you talk about things like that notion of like a tree sum, for example, like if we had a really rich topology, like I couldn't just talk about a tree sum, like I'd have to have all these caveats. But if I know it's like just like all nodes have the same type, namely that have a number that I could sum, that's great. Or if I know that there's several types of like there's dollars and times, maybe for dollars I could sum and for times I could do a max. And so that means I have multiple of those arrays, like one for the dollars, one for the times. And RDF, in theory, has a bit of that, and I actually like to think about RDF less like RDF and more like data log, if that kind of makes sense. Maybe for folks who are not familiar with data log, maybe it makes less sense. But the reason I bring that up is you can think of each RDF relation as a database or a database table to itself. And then what we could talk about now for the GPU perspective is, if I'm working, can I just do operations on one RDF triple in all instances of it? And that would be a very vectorizable or GPU friendly operation.
Kind of aligns with the last episode of the Graph Show with Scott Meyer on Liquid, which uses data logging.
Yeah, and that makes a lot of sense why. Like I've actually been playing with implementing Cypher on top of this kind of stuff. So it's in different languages you can map down, as long as ultimately you've got these nice, instead of thinking about rows, you want to think about columns.
So let's get back to the fraud use case. So we understand the use case. We kind of understand how to get the data into the the processing pipeline. What happens there, and how do we get from there to insights and GraphViz?
Yeah. So what we find is a lot of our users don't have a graph database. Like some do, and that makes our life easier because there are queries we could do there, and just there's less work to do. But that's a project that could be a 6-month project. So I would basically never recommend starting with the database. So what we see more normally is you have your transaction database, like your Redshift or your Spark or whatever, right? What the team will do at that point is like you could write a one-liner to get whatever, maybe your accounts or your transactions. So you get these tables. From there, what we would do is those tables, we built out basically helper libraries. Like you can do it manually, but we have helper libraries that let us turn them into graphs. So and we could do, I mentioned rapids, so we could do it. You could do it in pandas, you could do it in SQL, or you can write it in panda style, and then we happen to run it on GPUs because we're using rapids. And for example, let's say for transactions, let's say each transaction has, the person creating it, the person receiving it, maybe the credit card number. We would, in just a few lines of code, we could turn that into a graph. Say, hey, these 3 columns should be treated as nodes, everything else is treated as attributes. And then it'll automatically turn that into a graph representation.
And edges, I imagine, are treated like attributes, but
same thing. So exactly, we'll get a node table and an edge table. So can you take your transaction table and then that same transform, pull out these nodes, these columns as nodes, and then if there's a transaction that has this creator, this recipient, and that credit card number, they'll not only create those nodes but also create the edge table entries for that there's an event connecting them.
Okay. So what happens from there? But like I say, I'm very fuzzy on
Yeah. And so a cool thing,
embeddings.
I don't know when this episode precisely will come out. So, but we do have a Graphistry repo where we try to automate a lot of this stuff for you. And so let's say you do your Spark query or your SQL query. You run it through what we call in this case, the hypergraph transform. So again, it's just a one-liner with just picking out how you want to do the shaping. That will give you this your node table and your edge table, and then what you can do is treat that as the training data for your graph neural network. Now, there are different models of graph neural networks. In this case, for most fraud, one of the things that start with is again this thing called an RGCN, and so we kind of have these ready out of the box. And then
break down the acronym. What's the
RGCN? So it's a recurrent graph convolution.
Okay.
Yeah, network. Yeah, I'm stumbling on that. But yeah, like the important part is the R, which means that you can do heterogeneous data. So in there, if you have different types of nodes, different types of edges, like you have, so the R is about the different types. So like maybe we have accounts versus wallets. And then the GCN is these algorithms can take advantage of these attributes. I'm oversimplifying, but like it's a neural network.
Well, kind of oversimplifying my very sketchy understanding. You're kind of parallelizing the operations over the types and then recombining them, or how does that work?
So when we do that, each step here is parallel. So when you do the Spark query, that's like automatically parallel, just normal Spark, right? Or if we use Dask or Dask QDF, it could be on a GPU, same thing. It's just SQL, right? When we do that conversion, we're actually using those same data frame or SQL operations. So we'll actually do a bulk ETL on the GPU if you happen to have the GPU. So that's the graph conversion is like that. And then for the neural network, I think I know we're sticking with the fraud. Okay, I'll try to stick with the fraud case for the intuition.
Tangents are good.
Yeah, but it's basically in a fraud graph. It's almost like a social network for thinking like voting along a social network, where if there's like one bad credit card number, and that's kind of or there's like a few people using some bad credit card numbers, and then if you're transacting with one of those people or you're sharing a credit card with one of them, your transaction's probably bad too, right? So this is called label propagation, where we'll iteratively propagate the fact that there's some bad stuff going around. And so that's basically, and this is where graph neural networks start working a little differently from normal neural networks.
Any relationship with spreading activation? That kind of.
I'm not sure about spreading activation, like what that refers to.
I think we're probably talking about the same thing.
Okay, so yeah, so I think like for when we get into this stuff, like if we look at like maturity levels, what we see is a couple of things. Like let's say it was like a good team, right? Like somebody who had like a bunch of AI people and like a really, by good, I'm not saying that these are better people, just they had a lot more money and time, right? And so if they're at that point, what we might have seen is something like, they might have been doing something like for each transaction, so they have a transaction table and each transaction is just like a row, and so they're scoring rows. what they might have done before is like they might have had a neural network, or actually very often just like a random forest is doing really well with these different kinds of columns. So it's like, hey, if we're doing fraud, and let's say it's at a bank, and like every transaction's at $9,999, oh, that's like really near $10,000, but never goes over $10,000. This is probably somebody doing money laundering, like, because those are things that don't get reported, right? The graphs,
Reinforced being, a set of decision trees, right? So things that have been
yes,
captured by people working in the field. When this happens, often this happens.
yeah, you could do lots of little tiny rules. You can think of it that way, and then I'll just kind of blend them together for you. The reason random forest is always interesting is because it's not a neural network. And so as much as people say AI is basically neural networks, for business data, it's often tabular. And until very recently, that was generally neural networks, and AI generally did really bad on business data. Like it did good on, like we're talking about, like on finding cats in videos, which is like a perception thing. But business data is really like tables. And it just, when you had to do all these tiny rules, it just actually in practice wasn't working. And random forest was nice because it could kind of like blend all these little rules together automatically and figure them out and blend them together with those decisions you're talking about. What we're starting to see is that sometimes neural networks would help, like maybe you have a sequence of transactions, so something like an RNN would be good. And then bringing the graph world, maybe Tiger Graph is useful because remember we were talking about like maybe there's like a cluster of people that there's like a fraud ring upstream from this transaction. Maybe we could bring in a community label as part of that random forest. So one of the columns in our table might be the community that the transaction is part of. And so the graph is actually pre-processed before the AI. So that's up to like a year or two ago. That'd be kind of, if you had more money than time, you'd be doing that kind of stuff, right? Where the graph neural networks started to become really interesting is now all of a sudden, instead of using the neural network, but the traditional neural network or the random forest to blend all those features together, we can actually use the heterogeneous graph to blend it together. And so if we go, let's say for the fraud case now, we're looking more at like I was reading like an Ethereum paper today. We could have different kinds of accounts going on that are nearby. Like maybe there's a mixer that's kind of, let's say there's some mixer a couple hops out from where the money was coming from. That's very hard for something like a random forest or a neural network to see that several hops above was a mixer. But what a graph would be able to see is like, hey, out of these three incoming edges, there's some mixed tainted stuff. Out of those two incoming edges, there's some more traditional money coming in. But because so much of the incoming money was coming from the mixer, that's probably also suspicious. This is suspicious money flowing into you. And a graph neural network, and when we talk about label propagation, it could, when it's doing all that, those feature blendings, it could wait on that kind of stuff.
Sure. In terms of sort of more traditional graph database type insights, like shortest paths, for example, were pretty important in some of my past work. Like say you have two actors, you want to know, have they interacted before? Yeah, a pretty common thing to do for some fraud use cases. Is that something that would be handled naturally by say a random forest approach or other a GNN approach, or would you want to import those features from say a graph database that could find the shortest paths for you? And
so that's been interesting. Like we're getting involved in a lot of supply chain AI work, for example. Sometimes just we're working with Excel people who just want to see it. Maybe we'll talk about visualization at some point, but other times, like once they see it, then they want to like start doing predictive models and things. And so in supply chain, we're going to see a lot of shortest path. And so there, because you might want to look at like cost optimization, and the shortest path is like part of that. So like, and one of the biggest surprises for me from about a year or two ago was actually in this domain of shortest path and convex optimization and that kind of stuff. So about a year or two ago, Google Maps went public with the way they compute ETAs is now through graph neural networks. And then I think I was mentioning Meituan, like I think they actually do the same thing now as well, and likewise for the recommendations. And when the reason I was bringing up the supply chain, if you want to do like cost prediction, that's actually like whether it's an ETA at the end of the journey, or it's like what's the likely cost of going along a journey. So whether it's in time, dollars, carbon credits, it's actually the same thing. So yeah, we're seeing, while that might have made sense before in a graph database, we're actually seeing you want to, again, from whatever the database, do the bulk import into the GNN, and maybe the graph, like sometimes the graph could be nice, graph database could be nice for carving out the subgraph you want to train on, because a lot of this comes down to graph sampling, but it's not as essential.
Sure. So get us from the GNN to the visualization. I know you use GPUs also for GraphViz. Like following, yeah, if you can, like following the fraud use case. How do these insights get surfaced to operational folks? And
yeah, so we'll starting just like why we use GPUs for the visualization. Like over the last 10, 20 years, graphs were hard to to get GPU accelerated. Visualization has all sorts of things like histograms and clustering and all these things going on. And one by one, all of those were figured out. And so we're an end-to-end GPU platform, and so we could do visual stuff that a normal JavaScript-based toolkit just can't. We're also a little unusual where we'll run GPUs not just in the browser, but in the data center, sort of kind of like, imagine like a Netflix or Google Map where we can offload and stream in. And so visually as an analyst, if I'm going on, let's say the fraud case, we had a case where I'll just say top 3 cloud provider. They're curious about just some activity on their website and see if there's what was going on. And by being able to load in and visualize a lot more data, they're able to see things like botnets immediately. Like we didn't even find out about this until like about a year later or 2 years later, about like why that was like basically we won the POC on the first day. Like it's like, oh, oops, botnet. So being able to see a lot more data is really powerful. And then if going to your question, your allusion to what does this have to do with AI? Like, graph visualization is very algorithm driven. So clustering, automatic coloring, automatic sizing. Like we actually use a lot of algorithms to drive what's there today. But then from the user side, it lets people start thinking about what the AI should be doing, and whether they want to do an automation or they want to do an AI model. It gives them intuition for what it should be. So let's say we start seeing, here's this inauthentic account behavior going on in my system. Well, I could do certain types of manual graph rules. So I might want to run it on the graph database. Like, hey, if somebody's, just in a short amount of time doing a lot of stuff, I'm seeing this behavior common on my platform. The visualization makes it very clear. You could bake those as rules. Where the graph neural networks start becoming interesting here is like, hey, could I just learn those rules? Like if I have a lot of tickets that like we've shut down a bunch of these, can I start just automating that flow? And so now we're getting more of like, we want human in the loop where kind of the algorithms are working with the teams. And then also as the people building those, now all of a sudden the visibility is useful, not just for the people responding to incidents, but to the people building the models. Like, how do you get that intuition? Can you quickly see it? And then once there is an incident, sometimes there's like an automated handling, but let's say there's a bot and then somebody wants to then act on the bot alert. Sometimes you have an automatic shutdown, but let's say we're kicking users off the system. That could be a very hard action. And so maybe somebody wants to visualize it. They want to see what the algorithms are seeing. So it kind of works really well together.
Okay. You talked about democratization. I know you have a specific solution. It's called Graphistry Hub, right? But let's start maybe just generally around the problem of taking these types of workflows, which are normally found in big companies with, as you say, lots of time and money to spend, and making them more accessible to everyone else, to small companies, to developers, and so on. How do we do that?
Yeah. So big companies are made of lots of people. And even if there's a great like AI team somewhere at a company, that doesn't necessarily help anyone else in the company. That might just help their sphere of influence, right? And so what we find is a few things. One is, how far can you go with if you are not, some code, but not a lot, like how far you can go with just Python. And then if you don't even know that, or like, but you're really, that's not your cup of tea, how far can you go with no code? So that's one dimension. And then the other dimension is cost. Just if you want to get into whether it's in time, whether it's in compute resources. So the old days, think of like Hadoop. Let's say, think of when I met a lot of the first folks in the graph community, like early days of Tinkerpop and whatever. So back then, you'd get these massive ETL projects to get into the database projects. You have to get like these hardware resources. You have to get this data wrangling. And you've actually not really done anything useful at the end of that, right? Like only then do you start the actual business ROI of like, hey, that's where the intelligence and the action stuff starts, right? Am I making a visual insight? Am I making a decision procedure? Am I making an app that people can use? Like that all happens after all that stuff. So, luckily we're not in that era anymore. So this is the modern data stack era. So you already have all the maybe slower in terms of the query side, but you do have those databases. And so if you imagine big or small company where you have that, you have Salesforce and you have a CSV export, you've got your Redshift and you can do a SQL, right? Like that kind of thing. So what we're seeing is, for example, one thing where we're piloting is Power BI. Like, so, hey, you're in Power BI, you're doing your dashboard and you want to start getting graph insights. Great, can you just drop in a component and you're doing all like, kind of like how Tableau lets you do all this tabular insights. Can you just connect in on your data source, and even if it's tabular, and make those on the AI side, we are seeing I wanted to get way like we're driving to fully no code. We see some vendors saying they have no code, but they're basically lying, which is I normally don't like saying that, but they are, because what they're really saying is the users are building ASTs visually, which is still programming. Like that's not what no code means. They're still forcing you to do that. So what we're kind of our visual tool for the analytics era is no code. Like we really mean no code when we say no code. And
well, you mentioned types before. I mean, that's never no code, right? If you have to have a schema as an input.
Yeah. So I think that the first insight is the base model, like whether it's an export from your Salesforce or it's a table in your Redshift, your SQL, whatever, it already has column types, right? Like you've got your account ID, you've got your transactions. And so you're right that we do need to get some sort of graph model from that. And a non-low code, like a masquerading low code solution, say, here's your visual AST of do this transform, do that transform. That's still coding. That's in my previous life as a language designer, we could share drinks about why this is horrible. And but in our view, it's what we do is like say, hey, turn these columns into nodes, these columns into edges. We make it a very kind of visual picker. You get direct visual feedback of what you're doing. To me, actually, part of the power of graphs is you get that direct manipulation, so you can see what you're doing as you go. You don't have to do the AST stuff, and that's enough for us to actually, once we have that graph shape, that's enough to actually start doing the model work. Once the AI side comes in, now we have to talk about things like, is it supervised? Like if it's unsupervised, there's a whole thing. A lot of our work is actually unsupervised, so it's especially early on, which is just embeddings. So that's actually early on, that's enough to work with. Like, hey, this transaction similar to that one. Like, let's say, if you have one incident, you have one ticket, is that similar to other tickets based off of the text or whatever? That's enough to actually get that. We've done fun stuff like let's look at stock markets and do that. But then the supervised case, all that means is like, hey, we've seen some tickets before or some accounts before, so one of the columns happens to be labeled. You just need to tell us which column is labeled.
Sure. So yeah, I know you have a talk coming up at Data Day. Is that in sort of in this general theme? What's the topic of the talk?
Yeah, it builds on the blog post we had that kind of got popular about what is graph intelligence. So on one side, we're gonna go more into what we're seeing as how that's helping different business leaders and different departments, like how graph neural networks have already taken over academia. Like over half of it, basically, if there's a top AI paper, chances are it talks about graph neural networks somewhere in it. Now it's going to talk about how the different teams in industry, how and why they're using graph neural networks. And then the new bit here, and this relates to the Graphistry Hub and our GitHub open source repos. we're trying to do the open source and automatic graph AI. So that's not just the Googles of the world, not just the Airbnbs.
Nice. Okay. Looking forward to it. Thanks for joining us, Leo. This has been the Graph Show. Thanks for watching.
All right. Yeah. Thanks for having us. And for folks interested in this stuff, I encourage you, stop by the Graphistry Slack or just try one of our free accounts and drop in your favorite graph.
Or attend Data Day.
Oh yeah, we'll be at Data Day. Yeah. So if you're out in Austin, let us know.